Let's move to minerals. How are you going to identify minerals? And the answer is there are certain properties that you're going to try to use to identify them. Now, let's start out with one of the key properties, but it's not one that you can always see, and that is crystal form. So let's take this mineral, for example. So this turns out to be the mineral pyrite. And you'll notice, oh, look at that form. Cubes. Okay, and sometimes these cubes interpenetrate each other. That's something called twinning, but we won't worry too much about that. This is the mineral pyrite. You can see it also has a nice metallic luster. And here's a whole bunch of little crystals of pyrite. And if you look carefully, again, you'll see that little cubic structure here. And when you're looking for cubes, it turns out one of the things you want to do is you look for symmetry. And so let's look at it from this, on this corner. And you see actually an interesting thing about a cube is it has threefold symmetry. We're used to thinking about it as having four sides, but if you look at the corners, you see here's a face, and that's just like this face, and just like this face. And if we rotate it, you'll see those faces are equivalent. And so that symmetry turns out to reflect the internal cubic arrangement of the atoms in this pyrite. Let's move to another one. Okay, here's another very common mineral, the mineral quartz. And you can see that actually, if you look down on the top of this crystal, you'll see that there's hexagonal symmetry. There are two sides here that are opposite, two sides here, two sides here. You go around, you say, oh, that's what we call a hexagonal prism that represents these faces. And then there's another pyramid on top. And again, you can count 1, 2, 3, 4, 5, 6 faces on that pyramid. So this turns out to have this kind of crystal form because the atoms are arranged in a hexagonal pattern inside the mineral. Here's another one. And again, here you can see threefold symmetry, but it's not like the cube because we have this rhombohedral arrangement. So here's the best rhomb to look at. So you can see, boom, these angles are not 90 degrees, but they're actually around 120. And so, or 120 and 60. And so again, when you look at this, you can see threefold symmetry, but this has different symmetry than a cube because you don't have the twofold symmetry that you have or the fourfold symmetry if you looked at the edges or the faces of a cube. Instead, we've got this rhombohedral look. So the atoms here in this mineral are arranged in a rhombohedral structure, and this turns out to be the mineral calcite, calcium carbonate, and a very common mineral. Now, this is a specimen of quartz. This is a specimen of quartz. You can see again the six-sided symmetry, 2, 4, 6 in that prism. And turns out this lovely stone is also quartz. But what happens is that there are little imperfections. In this case, there are inclusions of other minerals inside the quartz, and that's what gives it the beautiful color. Those inclusions may only be a fraction of a percent of the total material, but since quartz would be clear if it had none, then that little bit of color shows up. The red undoubtedly comes from having a little bit of iron oxide that's been incorporated in very tiny little amounts. Okay, here turns out this is what's called smoky quartz, and it gets that color because it's been irradiated from adjacent minerals that are radioactive, and that leaves little holes in the lattice that trap light and make it look black. So color, sometimes it will be diagnostic, but often it can fool you. So you have to be very careful about using color as a way to identify minerals. So let's see. So far we've got crystal form. That's a good way to identify things. Color, a little shaky. There's another very important property called streak. This is a ceramic plate. And what I'm going to do is to take this pyrite, for example, looks gold. But if we run it across this streak plate, we'll break off little grains. So you press down, and what did we get? We got a black powder that came off it. So this is called streak. And you see that even though the mineral itself looks this beautiful golden yellow, that when you powder it up very finely, it looks black. Now, other things don't have streak. So how about the quartz, for example? Can't see anything. So clearly, quartz has a colorless streak.
Want to do hematite?
Okay, so here's another interesting mineral. Looks kind of blackish. Test the streak. Oh, it's black too. Now, one other property of this mineral is that in this case, you'd say, oh, looks kind of nondescript. And it's tiny little crystals that you can't see the crystal form of. But one thing you can do, oh, look at that. This is a little magnet. And so we see this rock is, or this mineral turns out to be very strongly magnetic. It's called magnetite, and it's made out of iron oxides. Okay, other ways to identify minerals turn out to be measuring the hardness. Okay, this is one of the main tools of a geologist. It's the hammer. And the key thing here is that it's made out of steel. And steel, you'd say, well, that's pretty hard. But how does its hardness compare to that of minerals? This is a great way to test what minerals you have. So let's take some of these minerals. And what I'm going to do first, let's take this calcium carbonate. And to test hardness, what you can do is see if it scratches something. So I'm going to take this calcite and run it across the hammer. And look, it seems to have left a mark. But if we brush it off, that mark is gone. Okay, that means that we made little powder out of this mineral, but we didn't scratch the hammer. So this mineral calcite is not as hard as the steel hammer, which has a hardness of about 5.5. There's a scale for hardness called the Mohs scale, and different minerals are assigned specific values. So let's try another mineral. Okay, how about the quartz? Well, let's take this little corner and run that across the hammer. Okay, we can see a little mark, but now that mark remains. There are two more marks. Again, that mark is still there. Okay, let's do one on this side too. Let's try it with the, so the quartz is harder than the hammer. This is that feldspar. And again, it's a little hard to see probably in this camera, but indeed, there's a scratch. And so the feldspar is harder than the hammer. Okay, what else can we use? Well, suppose we have glass. Let's try some of these minerals with glass. Now, glass is going to have a hardness a little over 6. And so first let's try the calcite. Oh, nothing, no mark at all. Okay, now let's try the quartz. Okay, and is that showing up?
Yep, I can see it.
Okay, so there's a nice little scratch. So the quartz definitely scratches this. Let's try it with this pyrite. Yeah, you have to use a moderate amount of pressure. Okay, so that doesn't rub off. There's another scratch. So the pyrite is also harder than the glass. So this is one way we can try to tell the nature of the mineral is by testing its hardness. Now, some other common estimates for hardness. Turns out your fingernail will scratch anything with a hardness less than about 2. Copper pennies, if it's really made out of copper, which is very rare for pennies these days. Most of them are made out of zinc, with a little thin veneer of copper. But copper has a hardness of about 3, and that's the way we can test hardness.
What's the hardness of steel?
Steel is about 5.5.
And glass is 6?
Glass is a little over 6.
Okay.
And it will vary a little bit from one glass piece to another, and also from one steel to another. You know, if you have steel files, those are usually made out of specially hardened steel, and so they may have a hardness up around 7. But you know, steel like in a hammer, this is a good test thing. You can use a nail, and that's got about the same hardness as a hammer, but it's hard to see what you're scratching with a nail. And you may be able to scratch the mineral with the point on the nail, but it's a little more difficult. Okay, now another important way of identifying minerals is cleavage. And so cleavage refers to whether or not a mineral will break and reproduce the same planes that you started out with. So this is a piece of biotite, and if you look at it edge on, you see, oh yeah, it looks like it's just thin sheets of a silicate mineral. Now, watch this, and I'll show you how it cleaves. If you get right in between these layers, you see that, oh, they break off, and they give you little flat sheets. Okay, and what do those sheets look like? Well, they're a plane. So biotite has cleavage, very good cleavage, and it has only one cleavage plane, which is this flat surface that you see here. Now, other minerals may have cleavage, but have more cleavage planes. And so we have some. So here's a mineral. You can see this has kind of cubic type symmetry, doesn't it? You know, you can see you've got, there's one plane and another plane and another plane, and they all come together at angles of 90 degrees. And so what I'm going to do is to take the hammer and very gently break this mineral. And look, you know, even though it came out kind of like a stair step here, you can see that flat plane reproduced. And here we've got more flat planes. Here we've got little bitty cubes. And again, all 3 of those cleavage planes reproduced. So when you're looking at this, you're actually not looking at the form, although sometimes when this grows, it will look like little cubes. This turns out to be the mineral halite. And one way of telling it is you can actually taste it, because halite is what your table salt is made out of. Sodium plus chloride, sodium chloride, 1-to-1 ratio. So cleavage is a great way to identify things. If we were to take this quartz and break it, turns out we would not reproduce these beautiful hexagons. Instead, we'd get these conchoidal, kind of dish-like fractures in it. And so quartz is not going to give you good cleavage. So cleavage is a great way of identifying things. I'll show you one other one, which we aren't going to break it because it's not easy to do. But if you look at this black mineral is the hornblende that was in granite. And if you look at the surface of this, you can see there are kind of little stair steps all over it. Is that showing up in the camera?
Yes, yeah.
Okay, and those little stair steps, if you look carefully, you'll see those are not at 90 degrees. Instead, they're at about 60 and 120. And so the stair step cleavage at those oblique angles tells you that you've got hornblende, coupled with, of course, the black color, which in the case of hornblende can be pretty diagnostic. So you look for, if you see two black minerals, you say, which is it going to be? Okay, one cleavage, two cleavage planes that are located at 60 and 120 degrees of angle. Okay, so we've got crystal form, we've got cleavage, we've got a few odd things. Oh, hardness. So and color to some degree. So those are the main things that you're going to be able to use in the field. But there are a few other things as well. We saw magnetism, and it turns out that this calcite. Oh, here we go. You can see the beautiful rhombohedral cleavage in calcite here. And one other thing that calcite will always do, if you take an acid, it doesn't have to be super strong. I think this will probably work with vinegar in your kitchen if you want to try it. But if you put a drop,
Yeah, right there.
you can see that the acid is reacting with the calcite and making little bubbles. Those little bubbles are carbon dioxide because calcium is made out of calcium carbonate. And when we introduce acid, it reacts with the mineral to release the CO2, which makes the little bubbles. So I guess if it was all neutralized, we could have it as a carbonated beverage, but I don't recommend that you try that. Okay, so those are some of the main ways of distinguishing minerals. And ultimately, when you get a rock, and the rocks that you've all found, you're going to look at the minerals inside these. So those are going to be homogeneous regions. In this case, it's pink. In other cases, it's black, or it's gray. The gray stuff, again, quartz. The pink stuff here is potassium feldspar. The gray, or the black stuff is hornblende.